October 2025 stands out as the initial instance in documented records where a pair of distinct celestial bodies are hurtling toward the sun from entirely separate starting points. The 3I Atlas probe verified that this interstellar drifter bears a chemical makeup defying conventional theories of starbirth. At the same time, SWAN R2 has intensified in luminosity so abruptly that its makeup differs markedly from typical items in our own Oort cloud. Their joint trajectory forms a stellar bottleneck event that's statistically expected only once in several million years. Nevertheless, they're both set to brush past the sun just 28 days apart. Mission controllers are monitoring their paths with unerring accuracy. Detection gear is picking up molecular irregularities that upend long-held principles in comet research. Yet the intrigue deepens here. As these bodies plunge further into the sun's blinding radiance, our observatories will lose all visibility right at the pivotal moments of their passages. Could this alignment be more than chance? Might some force prefer we stay in the dark? Stick around while we delve into the reasons October 2025 might overhaul our understanding of the true dynamics unfolding in the cosmos. Part 1. Twin Beacons Overhead. A duo of unfamiliar entities has entered our solar neighborhood. One lean and fast, edged with an eerie emerald sheen, the other vast and radiant, deploying a tail that spans vast swaths of the heavens. They originated from remote sectors of the universe. Still, they're aligning toward our star in a stellar ballet, prompting stargazers to verify their models repeatedly. The initial arrival showed up on July 1, 2025, within the electronic gaze of the Atlas Survey Scope, in Chile, a lone speck of illumination where none belonged. Shortly thereafter, Path Dynamics unveiled the reality. This entity, labeled 3I Atlas, follows a hyperbolic route unbound to our sun. An interstellar nomad marking the third verified intruder from past our system's boundary. The follow-up surfaced mere months afterward, fading in from the sun's haze like a specter at first light. Comet C225R2, spotted in SWAN observations on September 11, 2025. Visible to the naked eye with binoculars and already flaunting a tail that backyard skywatchers deemed spectacular. Within the crisp corridors of NASA's Jet Propulsion Laboratory, processors buzz with ongoing streams of sensor feeds. Antennas spanning the planet pursue these intruders with the steady rhythm of a pulse. Every batch of info weaves a narrative. Luminosity trends, light spectra, path adjustments fine-tuned to a fraction of an astronomical unit. Yet, raw figures, no matter how exact, fail to convey the spectacle unfolding in the evening vault above. Step out on a crisp October night, clear skies and distant from urban light pollution, and you could catch sight of them. 3I Atlas shows as a hazy patch via a basic scope, its verdant hue faint yet evident to experts. SWAN R2 commands the post-dusk western sky, its appendage arcing skyward like a stellar flourish on the twilight canvas. The gear communicates in inaudible bands. The rapid clicks of image sensors snaring light particles journeyed across eons to arrive. The soft hum of analyzers breaking down celestial rays into basic components. Observatories around the world transmit their insights in cascading info flows to hubs where experts grapple with decoding the visions from their tech. But the void endures in quietude. No noise traverses the emptiness linking realms. Solely waves of energy span the divide, bearing details hidden in light's hues that reveal these visitors aren't entirely as they seem. 3I Atlas advances with the deliberate velocity of an entity certain of its destination. Its course will draw it nearest our sun on October 29, 2025. Positioned at 135 astronomical units from the sun, right on the inner edge of Mars's path. For something hailing from beyond our solar system, that's an impressively near pass. Near to the point where certain folks are starting to pose some troubling inquiries. SWAN R2 sticks to its personal timeline. It hit perihelion back on September 12, 2025, swooping into just 0.5 astronomical units from the sun prior to heading back outward, yet its nearest brush with Earth arrives afterward, on October 21st, as it zips by at a mere 0.27 astronomical units from our planet. On a universal scale, that's almost like grazing our air layer. It's this schedule that has stargazers burning the midnight oil, glued to their monitors well past when everyone else has clocked out. A pair of entities from utterly distinct backgrounds zeroing in on the heart of our solar system mere weeks apart. The odds, according to probability calculations, indicate this ought to happen only once in a blue moon. Still, we're right here, observing what could rank as the wildest alignment in all documented skywatching lore. Or maybe it's no fluke whatsoever. The emerald hue of 3I Atlas has drawn special scrutiny. Spectral scans detect diatomic carbon and cyanogen compounds that glow green under sunlight's influence. Perfectly ordinary for a comet starting to vent gases as it nears the sun. However, the vividness and uniformity of that shade have got experts, those who've dedicated lifetimes to tracking these starry drifters, scratching their heads. Swan R2 brings its share of enigmas too. The way it flared up quickly after slipping out of solar conjunction points to a makeup that's far from the norm for icy bodies from our own Oort cloud. Its tail formation mimics known behaviors, but with an odd twist, like it's adhering to directions penned in an unfamiliar dialect. Size plays a huge role out there, and the disparity between these intruders couldn't be starker. 3I Atlas shows up as a sharp beam of brilliance, tight and deliberate. Estimates now put its core at maybe a few kilometers wide, unremarkable for comet cores, but plenty to spark the outbursts we're seeing. Swan R2, on the other hand, unfurls over the heavens like a glowing shroud. From our vantage, its hazy envelope and streaming tail stretch across multiple degrees. We're stepping into October 2025 with a duo of stellar intruders hurtling toward their tightest meets with the sun. Mars snags prime viewing of 3I Atlas on October 3rd as the rusty world's route pulls it to within 30 million kilometers of the extrasolar nomad. The probes we've stationed in Mars orbit, equipped with lenses and analyzers, will pivot their gear to capture this incoming guest, collecting insights that might at last tackle the riddles piling up from every new look. October poses its own headache, though. With both bodies nearing their solar flybys, our planet's line of sight gets trickier by the day. Intense sunlight will soon engulf the pair, rendering earthbound scopes useless right when their paths get most intense. For weeks, maybe longer, they'll vanish from view completely. Once they swing clear of the sun's glare, if they do, what tales will the detectors reveal? Will they reappear unscathed, marked just by the usual toll of sun grazing? Or might they haul back signs of deeper secrets, ones that upend how we grasp the wanderers cruising interstellar voids? The puzzle gnawing at these autumn evenings seems straightforward on the surface, but it's tangled beyond measure. Could it be merely a comet, a bastion, or an answer to a signal we didn't realize we'd broadcast? The cosmos has dangled two riddles overhead, and this October 2025 might offer our sole shot at cracking them before they fade back into the void's embrace. To grasp this, though, we must first trace how we spotted them, and crucially, how they zeroed in on us. Part 2. Instruments that murmur. The detection of cosmic. The journey of celestial visitors doesn't kick off with a flashy unveiling, but through the steady gathering of light particles on digital detectors positioned around the globe. Night after night, robotic observatories sweep over selected regions of the heavens, their digital lenses snapping photos that algorithms will analyze, refine, and inspect for anything out of the ordinary. The Atlas survey, which detected 3I Atlas, runs 4 observatories distributed over 2 continents, each fitted with lenses able to track enormous sections of the sky at once. On every cloudless evening, they produce hundreds of gigabytes worth of information, with millions of star locations pinpointed to remarkable accuracy. The identification of an interstellar intruder arises from this torrent of data as a lone, unusual speck of brightness that shifts too quickly and off course. Yet, Atlas forms only one part of a worldwide symphony of robotic watchers. The Catalina Sky Survey in Arizona, Linear in New Mexico, NEO-eyes circling far above Earth's air, all feed into a web of vigilant observers that stay alert around the clock, without pause or oversight, catching every alteration in the universe's rhythm. When SWAN R2 showed up in the records from the Solar and Heliospheric Observatory, it wasn't NASA's expert stargazers who first picked it up. Hobby astronomer Vladimir Bezugly, reviewing SWAN imagery for his personal studies, caught the odd flare-up that turned into one of 2025's most dazzling comets. That's the essence of contemporary astronomy. Experts and enthusiasts, electronic detectors, and personal instincts collaborate to seize those brief instances when a fresh arrival graces our stellar surroundings. The tools murmur their revelations in terms of light measurements and pixel brightnesses. Yet it requires human perception to discern when those murmurs signal something remarkable. Various tools uncover distinct insights into these heavenly intruders. Optical lenses display the general form, the glowing core, the growing envelope, the trailing streamer that bends from the sun like a stellar wind indicator. But to grasp their true nature, we must split their illumination into its basic wavelengths. Spectroscopy converts celestial glow into knowledge. As compounds in a comet's envelope soak up and release sunlight, they leave unique signatures in the light spectrum we observe. The very large telescope scans of 3I Atlas uncovered surprising elements. Robust signals from cyanogen and, more unexpectedly, from nickel particles shining in the emptiness of space. Nickel isn't entirely new to comets, but its prominence merits notice. Even more puzzling is what the VT overlooked: iron signals that usually pair with nickel in typical materials. The lack of iron alongside the bold nickel mark forms a molecular profile that strays from what we'd anticipate from comet origins and development. The James Webb Space Telescope directed its heat-sensing gaze at 3I Atlas in August 2025, showing a makeup heavy on carbon dioxide but light on water gas, especially given the great distances of those scans. This aligns with a comet featuring outer shells loaded with easily vaporized frosts that activated cooler thresholds, sparking displays well before water frost plays a major role in the visible envelope. SWAN imagery offers a fresh angle. The Solar and Heliospheric Observatory's SWAN device charts the spread of hydrogen particles born from water molecules shattered by the sun's UV rays. This yields a spatial picture of water gas dispersing in the void near lively comets, exposing features hidden from standard scopes. The Hubble Space Telescope contributed high-resolution images limit the dimensions of 3I Atlas's core to maybe just a handful of kilometers in width, large enough to account for the detected outbursts, yet compact enough to avoid notice until it had ventured deep into our solar system. Every new sighting contributes yet another fragment to an enigma that becomes increasingly intricate with each batch of information. Yet tools of observation can mislead just as readily as they illuminate. The software routines that sift through telescope photos are built to spot familiar configurations, the routine paths of bodies adhering to Keplerian paths around the sun. If an entity deviates slightly from the norm, such anomalies might get overlooked by the exact routines intended to interpret the findings. Think about the difficulties in tracking luminosity shifts. Comets fail to intensify uniformly while nearing the sun. Rather, they display intricate fluctuations influenced by the vaporization of various frozen materials at varying ranges, the spin of unevenly formed cores, and sporadic ejections of particles and vapors from dynamic zones. Separating routine fluctuations from truly irregular actions demands meticulous scrutiny from specialists versed in the nuanced aspects of cometary dynamics. The emerald hue detected in 3I Atlas exemplifies this intricacy. Numerous compounds can yield green glows amid the environments of cometary atmospheres. Diatomic carbon stands out as the primary offender, glowing green upon stimulation from sunlight. Cyanogen may also play a role in such hues. Lacking detailed spectral analysis to pinpoint the exact compounds involved, the verdant shade offers hints but no firm conclusions. Press accounts of atypical celestial finds often escalate ambiguity into hype. When early dispatches highlight unforeseen molecular traces or odd path features, these elements can morph into proof of sensational theories well ahead of any rigorous evaluation to confirm or dismiss the preliminary data. Science's methodology aims for inherent refinement. However, such adjustments typically unfold at a pace slower than the urgency of societal curiosity for resolutions. Herein lies the pivotal role of these devices, not merely as spotters of interstellar events, but as grounding forces amid waves of conjecture. Observatories remain indifferent to our craving for thrilling revelations. They merely capture light particles and chart locations, amassing a repository of records that will ultimately uncover the reality of these intruders. Security factors introduce yet another dimension to these examinations. 3i Atlas and SWAN R2 both trace courses that maintain ample separation from our world. 3i Atlas comes no nearer than 8 astronomical units, roughly 270 million kilometers. SWAN R2 draws as close as 0, and 27 astronomical units, exceeding 40 million kilometers distant. Far from endangering Earth, these represent chances to examine entities born under circumstances far removed from those of our own system. The pressing issue at hand is the timeline. As October 2025 advances, these interlopers will plunge further into the sun's blinding radiance from terrestrial viewpoints. Earthbound scopes will forfeit their capacity to follow during the most compelling stages of solar passages. Orbital platforms perform superiorly, yet face constraints on allocation and must weigh these subjects alongside competing research agendas. From this symphony of machinery arises an image composed of data markers and emission spectra, trajectory parameters, and luminosity graphs. Yet images lend themselves to diverse readings, and the query persists. What if the initial illusions stemmed from the devices themselves or the preconceptions of those interpreting their outputs? The scopes will persist in their steadfast watch, gathering light quanta and logging coordinates with unerring accuracy. But as these arrivals descend sunward, the faint murmurs of the instruments will. The signals begin to dim, prompting us to ponder the enigmas concealed within the expanding quiet. Section 3. The Dialect of Metals. The vast expanse of space communicates through the lexicon of particles, with 3i Atlas narrating a tale composed in an unforeseen idiom. As the Very Large Telescope directed its advanced spectrographs at this cosmic wanderer, it uncovered an anomaly that caused scientists to hesitate and revise their assumptions. Nickel gas shimmering in the almost empty void near the comet's core, without the accompanying iron signals that were anticipated. Within spectroscopy, each substance inscribes its mark through illumination. Upon excitation from sunlight or particle impacts, atoms release light particles at precise frequencies, signatures as distinct and recognizable as personal genetic codes. Nickel particles generate spectral lines in the verdant range, enhancing the ghostly hues that have turned 3 Atlas into a prized subject for stellar photographers. Yet nickel seldom journeys solo through the stars. Among space rocks, planetary fragments, and the rare icy bodies where it's been spotted, nickel usually pairs with iron in proportions echoing the atomic reactions that created them in ancient star hearts eons past. The elemental distribution etched in the table of elements implies that nickel's presence demands iron in reliable amounts. 3i Atlas appears to have skipped that key lesson in cosmic makeup. The VLT data gathered while the comet neared its August 2025 maximum glow showed vivid nickel spectral peaks rising sharply from the ambient light profile. Those same scans hunted for iron and detected virtually none. The detection thresholds were so stringent that standard stellar ratios would have made iron straightforward to spot. This compositional quirk has inspired a range of hypotheses, all striving to align the findings with established science. Maybe resilient nickel-infused organics, enduring the chill of deep space, decompose selectively when warmed by the sun, freeing nickel first. Or perhaps eons of cosmic erosion have reshaped the outer layers of this nomadic ice chunk in manners beyond our current grasp. The cosmos owes nothing to our preconceptions of elemental conduct. Comet 2i Borisov, the prior extraterrestrial guest, revealed its unique quirks under scrutiny from Earth's premier observatories. Its carbon monoxide versus water proportions strayed markedly from those of homegrown solar system comets, hinting at origins in a frostier, carbon monoxide-abundant zone near its home star. Yet, 3I Atlas elevates these compositional surprises to even more captivating levels. Infrared scans from the James Webb Space Telescope exposed a makeup led by carbon dioxide, with steam contributing an unexpectedly small part at the vast ranges of those readings. Such a sequence, carbon dioxide spearheading the sublimation sequence, trailed later by water as the comet draws nearer to the sun, points to a stratified, bulbous build with the easiest to vaporize frosts on the surface. Cyanogen, the compound probably behind most of the verdant glow, enriches this molecular sketch further. Prominent CN spectral lines emerge in the data, aligning with organics fragmenting under solar UV rays. However, the intensities of various spectral traits deviate slightly from those in local solar system comets, indicating nuanced variations in makeup or form. The emerald shade, drawing widespread fascination, holds its own riddles. Although double-bonded carbon gets frequent credit for the green glow in comets, the exact compounds driving 3I Atlas's The Verdant Radiance of Atlas continues to puzzle observers. Cyanogen plays a role in generating that green light, so do specific energized forms of carbon compounds. Absent ultra-precise spectral analysis to pinpoint the exact sources, this emerald hue stays intriguingly vague. Such molecular indicators weave a tale that defies easy categorization. If individual atoms serve as alphabet characters and molecules as vocabulary terms, then 3I Atlas crafts its message in a lingo rich with carbon dioxide and laced with metallic nuances that stray from earthly linguistic norms. This blend aligns with scenarios of comet birth near distant suns, yet it's quirky enough to draw the scrutiny it deserves. Emission levels of various gases offer further insights into the intruder's essence. As 3I Atlas draws nearer to the sun, the output of diverse compounds ramps up steadily as proximity shrinks. This mirrors the standard behavior of ices turning to vapor. The nearer it gets, the faster those trapped volatiles shift from solid state to gaseous state. Experts grasp the equations behind this transformation, allowing forecasts of upcoming vigor from today's data. Still, amid this foreseeable pattern, faint irregularities linger. Proportions among molecular types fail to align perfectly with simulations drawn from our solar system's icy wanderers. The light intensity profile reveals fluctuations, hinting at uneven makeup on the core's exterior, or maybe targeted vapor releases sparked by hidden internal dynamics we can merely speculate about. Enthusiast stargazers have played a key part in unraveling these elemental enigmas. Crisp photos from hobbyists globally capture shifts in the hazy envelope and tail shape as 3I Atlas nears its closest solar pass. Such records fill in time gaps that pro-observatories, hampered by scheduling constraints and rival projects, simply can't cover. Online platforms have boosted select facets of these oddities, at times morphing early findings into hype-filled stories that race ahead of the evidence. Take the nickel-iron finding, for example. Some have spun it as proof of engineered origins, like forged metal parts instead of naturally gathered ones. That view demands wild jumps far beyond what the light spectra truly indicate. NASA sticks to its stance. The data fits a typical cosmic interloper, though one sporting quirky yet not unheard of compositional traits. Experts at the agency stress that such oddities make sense for bodies forged by alien suns, where varying heat, force, and raw materials might yield mixes alien to our neighborhood. The European Space Agency, via its probes and earthbound watches, echoes this view. While noting the spectrum's peculiarities in 3I Atlas, ESA team members point out that the core mechanics of comet behavior vaporizing ices, birthing the seen gases and particles, offer a solid lens for these sites, no need for far-fetched theories. Yet inquiry advances by probing quirks, and 3I Atlas dangles sufficient chemical riddles to occupy scholars for years ahead. The nickel glows, the CO2 prevalence, the cyanogen traces, the leafy tint, each detail slots into a mosaic that could reveal as much about star system births as about this lone guest. As October 2025 unfolds and 3I Atlas heads toward alignment behind the Sun, chances for in-depth light breakdowns are fading. The mix of growing separation from Earth, the diminishing solar elongation will soon render ground-based observations unfeasible, at least until the comet reappears from behind the Sun several months from now, assuming it does so at all. If we view chemistry as a form of language, we're deciphering a variant composed of ice and metal that reveals the circumstances of its origin, possibly hundreds of light years away. Whether this structure adheres to the principles of physics and chemistry as we know them, or suggests a more intentional design, stands as the core enigma of our autumnal heavens. The atoms reveal truths, yet they don't always disclose every detail we're eager to uncover. Part 4. Two trajectories, a single rhythm. Envision the solar system as an immense mechanical device where planets carve their reliable elliptical paths around our central star. Meanwhile, lesser entities, asteroids, comets, and rare interstellar travelers pursue routes that cross and separate in line with the equations of gravitational forces. Now, consider two intruders entering from utterly distinct angles, adhering to entirely separate orbital patterns, but synchronizing their nearest passages to the Sun mere weeks apart. The odds of such alignment ought to be extraordinarily slim. Nevertheless, here in October 2025, we're witnessing this very phenomenon play out overhead. 3I Atlas materialized from the vicinity of the constellation Ophiuchus in early July, its detection signaling the point when this extrasolar guest had grown luminous enough for our robotic sky monitors to spot. Its path follows a hyperbolic arc, the telltale indicator of a body unbound by our Sun's gravity. With an orbital tilt of roughly 175 degrees, it moves backward compared to the planets, entering our system from below the ecliptic, like a stellar fish battling the flow of orbital currents. Swan 2R presents an altogether contrasting narrative. This entity falls into the category of long-period comets intruders from our own Oort cloud that linger in the frigid fringes of the solar system for ages until gravitational tugs draw them inward, where the Sun's warmth awakens them. It surfaced near the constellation Virgo, breaking free from the solar brightness that had concealed it on its inbound journey. The configurations of their detections offer vital insights into each object's character. 3 Atlas stayed concealed until it had penetrated deep into our system, as extrasolar arrivals hail from random bearings and frequently traverse sky zones too near the Sun for practical viewing over months or years. When Atlas identified it, this stellar drifter had already surpassed Jupiter's orbit and started displaying initial traces of cometary behavior. Swan 2R grappled with a separate viewing challenge called the Hulitz effect. Comets with extended periods typically surge in brilliance nearing the Sun. However, this intensification happens when they're still at tight angular distances from our star as observed from Earth. They stay shrouded in solar radiance until their paths shift them sufficiently away from the Sun-Earth line to emerge in evening skies, precisely as occurred with Swan 2R in September 2025. The overlap in their pivotal moments forms a celestial timetable that seems almost orchestrated. Swan 2R hit perihelion on September 12th, plunging to just 0.5 astronomical units from the Sun. 3I Atlas will execute its nearest pass by Mars on October 3rd, coming within 30 million kilometers of the reddish world. 3I Atlas attains its perihelion near October 29th or 30th, drawing as close as 1.35 astronomical units to our star. Swan 2R's minimal distance to Earth arrives around October 21st, when it will skim within 0.27 astronomical units of our planet. This grouping of crucial occurrences, stretching such occurrences within a mere 6-week span, pushes the limits of mere chance. Were these incidents scattered evenly over time at random, the odds of such a precise temporal alignment would be vanishingly small. Yet, the principles of statistical mechanics remind us that highly improbable happenings turn almost certain over vast timescales and with enough chances. In a cosmos teeming with billions of comets and sporadic interstellar intruders, We might just be catching one of those uncommon instances where fortune aligns in surprising ways. The differences between our celestial guests go well beyond their sources and paths. 3I Atlas shows up as a slender streak of brightness, its outbursts limited to a compact area near its core. Recent calculations indicate a core possibly spanning several kilometers across, big enough to produce the noted envelope and streamer, yet humble beside the grandest icy wanderers in our solar system. Swan R2, by contrast, unfolds as a grand interstellar display on a wholly grander scale. Its envelope covers degrees across the heavens when seen through field glasses, and its streamer has stretched as far as 2 degrees, according to seasoned skywatchers. This equates to a vast physical extent reaching millions of kilometers. A gossamer framework, so fragile that its thinness rivals the emptiness of a lab vacuum, but detectable over interstellar voids thanks to the immense expanse it fills. Their shared spectacle unfolds amid Earth's shifting seasonal canvas. As fall advances in the north, both wanderers dip closer to the evening's western skyline. Swan R2 commands this starry stage, readily spotted by anyone armed with good binoculars and an unobstructed gaze toward Virgo. 3I Atlas demands more dedicated gear for spotting, though its greenish hue renders it distinctive once pinpointed. Still, October delivers hurdles alongside prospects. The very alignments enabling these near-sun brushes also plot to hinder thorough scrutiny. As the pair nears their closest solar points, they plunge further into the sun's blinding glow from our vantage. Earthbound scopes will soon forfeit the chance to follow them through the most intriguing stretches of their voyages. This viewing void amounts to more than a mere setback. It carves a hole in our insights that could prove vital for grasping these intruders' true nature. In the periods when terrestrial instruments can't peer at them, both will face their fiercest solar roasting. Should any oddities emerge or concealed traits surface, they're bound to unfold amid those unseen intervals. The backward path of 3I Atlas introduces extra intricacy to its path dynamics. Bodies traveling counter to the planetary flow endure distinct gravitational tugs, which might subtly yet detectably alter their future routes. Such influences could help pin down the intruder's size and makeup, assuming we monitor it precisely enough on either side of its sun flyby. Mars acts as our advanced sentry for 3I Atlas's October 3rd nearest pass. The Crimson World's fleet of circling probes, built to probe its atmosphere and terrain, will redirect their sensors at this fleeting guest. The sightings will be improvised rather than scheduled, yet they could offer our soul-sharp glimpse of 3I Atlas amid its pivotal sun encounter. The European Space Agency has revealed intentions for Mars-side monitoring via the ExoMars Trace Gas Orbiter and fellow satellites circling the ruddy orb. These vessels bear analyzers and cameras capable of unveiling subtleties hidden from telescopes on Earth. The observational alignment from Mars promises to be advantageous during the close pass, delivering insights into the comet's coma formation and tail evolution that enhance our ground-based views. Even with diverse angles and advanced tools, core mysteries persist unresolved. The serendipitous overlap in their arrivals keeps intriguing scientists dedicated to the probabilistic nature of solar system motions. In a universe where random meetings unfold over eons, what explains the near-simultaneous appearance of these two strikingly distinct intruders? When orbits echo one another, does it signal artistry or intention? Part 5. Ideas mapped out like star patterns. Human brains function as pattern-hunting devices, shaped by evolution to impose order on disorder and intent on chance. Faced with a pair of interstellar arrivals nearing our sun mere weeks apart, exhibiting odd traits and paths that appear nearly scripted, those brains start weaving tales that stretch well past the evidence at hand. These accounts span from the simply unusual to the truly astonishing, each providing a fresh perspective on the October 2025 encounter. The Scout and Fortress idea casts 3I Atlas as a cutting-edge scouting device, agile and versatile, assigned to evaluate our solar system's assets and safeguards. In this framework, Swan R2 acts as the primary outpost, a portable hub or signal hub equipped to sustain prolonged activities in our inner solar system. Their synchronized timing stems not from luck, but orchestration. marking stages of a broader campaign launched years or centuries earlier amid the frigid voids among the stars. An upkeep mission theory posits that both entities belong to an age-old network, self-operating mechanisms adhering to routine schedules to repair gear or refresh code dispersed across our regional stellar zone. 3I Atlas could transport code patches or spare parts, whereas Swan R2 supplies the production facilities or energy supplies required for significant system upgrades. From this angle, our solar system ranks as just one halt on a standard maintenance circuit. The vintage surveillance notion envisions these arrivals as survivors of a surveillance grid set up eons ago by a society wary of evolving hazardous intellects in their stellar vicinity. With our radio signals seeping into the void over the last 100 years, inactive mechanisms may have stirred, sending out both scouting units and heftier installations to gauge the risk posed by advancing human tech. Arguably, the most daring, certain views hold that these bodies form a retort to our species' inadvertent cosmic broadcast. Our radio and TV signals, radar arrays, and orbital transmissions have radiated outward at the speed of light for generations, forming an expanding sphere of electromagnetic traces encircling our world. Should any entity or force have tuned in, 3I Atlas and Swan R2 could embody their rejoinder, not appearing by happenstance, but as a calculated reply to our tech maturation. The leftover tech theory contends these could be relics from human society, dispatched in a forthcoming age when our offspring master star travel, then propelled backward in time or via paths timed to reach precise points in our history. Their peculiar composition and path behaviors might echo fabrication methods or material advances surpassing our present grasp while still bearing clear human roots. Legendary readings link them to timeless tales of sky omens, comets, and bizarre sky events that heralded pivotal historical. Every society across the globe possesses myths about celestial light signaling the ascent and decline of empires, the arrival of seers, or the close of epochs. It's possible that 3I Atlas and Swan R2 embody a contemporary version of these timeless motifs, acting as interstellar markers that delineate one phase of humanity's progress from the subsequent one. The interplay between predator and guardian presents a darker viewpoint. Should 3I Atlas signify a peril, perhaps a military apparatus or exploratory device, Swan R2 could serve as a countermeasure launched by the originating society to curb their creation's risks or sent by an alien entity to avert the hazard from approaching our world. Their alignment in October 2025 transforms into an otherworldly arena, positioning our planet as an innocent stake. Such hypothetical models attract interest in part because they highlight a key shortfall in traditional stargazing: the belief that odd occurrences demand prosaic origins. While this belief has advanced knowledge effectively, fueling breakthroughs in star life cycles and gravitational singularities, it nonetheless fosters oversights. Regions where unconventional ideas are rejected, not due to opposing proof, but simply for straying beyond endorsed paradigms. Avi Loeb, the Harvard stargazer who drew worldwide notice for proposing that Oumuamua might be engineered, has applied comparable reasoning to 3I Atlas. He highlights the atypical molecular traces, the exact moment of sunward passage, and the evident synchronization with Swan R2 as clues pointing to engineered rather than organic sources. His case underscores that bold assertions demand robust proof, yet robust proof, once present, merits thorough scrutiny. NASA alongside the European Space Agency adopt cautious stances, stressing that existing data aligns with organic causes even amid their peculiarities. Experts from these bodies observe that our catalog of extrasolar intruders is remarkably limited, merely 3 verified instances in the last 6 years, complicating efforts to define typical versus irregular traits within this group. This clash of views mirrors broader inquiries into research practices and proof's essence. At what point does an anomaly warrant exploring theories that upend our core views of the cosmos? In what way should we weigh methodical restraint against the peril of overlooking truly transformative findings? Press reports have heightened select elements of these discussions while minimizing others, The finding of nickel-absent iron garners frenzied buzz across online networks, frequently paired with guesses about fabrication techniques or production marks that exceed the actual implications of the spectral analysis. In contrast, the substantive enigmas surrounding 3 Atlas, its peculiar volatile makeup, the meticulous path alignment, the linkage to Swan R2 garner scant focus, even though they rest on firmer empirical foundations. The mindset behind conspiratorial notions also influences how these ideas evolve and proliferate. People naturally attribute purpose and design to chance happenings, especially those bearing weighty consequences for what's ahead. The notion of intentional interstellar envoys, as opposed to fortuitous drifters, fulfills innate yearnings for purpose and mastery amid a seemingly disordered cosmos. Past examples offer both warnings and inspiration for unconventional readings. Each major upheaval in astronomy, from heliocentrism to dark matter realms to worlds beyond our system, first encountered doubt from entrenched scholarly circles. History demonstrates that bold assertions lacking robust proof often slip into oblivion, serving as warnings against hasty conjectures. The convergence in October 2025 provides a chance to evaluate these rival ideas using actual observations. Should 3I Atlas and Swan R2 prove to be ordinary comets adhering to standard physical principles, their actions near perihelion ought to align with proven theories on ice vaporization and particle release. On the other hand, if they embody something unusual, any irregularities in their patterns should surface during their nearest solar encounters. Yet, a significant challenge arises. The intense sunlight that renders these solar flybys so compelling for research also renders them tough or outright impossible to monitor from our planet. In the key moments of their sun-grazing phases, both entities will vanish from view of Earth-based observatories, forcing us to deduce events from their state upon reappearing from the solar glare, assuming they do reappear. This blind spot in monitoring allows unchecked conjecture to thrive without factual constraints. Without immediate data, every notion gains traction, every explanation seems credible. The quiet period in October could reveal insights into our mindset as much as into these stellar intruders. No matter which perspective ultimately holds true, the meeting of 3I Atlas and Swan R2 signals a true advancement in science. Be they mere frozen wanderers or entities of a more peculiar nature, they broaden our grasp of the voids among stars and the occasional arrivals in our stellar vicinity. The narratives we weave about them reflect our aspirations and anxieties just as vividly as the entities themselves. And maybe that's fitting. Could it be a comet, a bastion, or an answer to a signal we didn't realize we'd broadcast? Part 6. 3I Atlas, Discovery and Path. The tale of 3I Atlas starts with a lone pixel shifting in intensity on a CCD sensor amid the Atacama Desert in northern Chile. On July 1, 2025, this cosmic drifter grew luminous enough for our automated celestial scans to separate it from the unchanging starfield that has endured in place for ages. The Atlas Survey Asteroid Terrestrial Impact Last Alert System employs 4 automated scopes mainly aimed at spotting risky asteroids that could endanger our world. These automated watchers methodically sweep the heavens, cross-referencing each evening's data with records of recognized bodies to flag any shifts, increases in shine, or new arrivals in empty patches. When the Atlas scope at Riuardo recorded that initial sighting of 3I Atlas, the item showed up merely as a dim blur drifting amid the fixed stars. However, movement across the cosmos narrates volumes, and mere hours after its detection, trajectory computations uncovered something remarkable. This arrival followed a hyperbolic course free from our sun's pull. The principles of celestial motion classify all sky objects into 2 core types: those native to our system, tracing oval routes that loop them back to their origins, and transients slicing through on hyperbolic arcs that swing by our sun once before vanishing into the interstellar expanse eternally. 3A. Atlas squarely fits the latter group, establishing it as merely the 3rd verified interstellar guest in human annals. Its path details a voyage originating from the gaps between stars. The route features a tilt of roughly 175 compared to Earth's orbital plane, indicating it nears our solar. The interstellar intruder emerges from below the ecliptic plane, moving backward against the orbital paths of the planets. This retrograde path marks it as an outsider originating from another star system under alien physical environments, which journeyed across the vast emptiness between stars for eons before entering our solar domain. The story of its detection highlights how narrowly we escaped overlooking this cosmic traveler altogether. Interstellar visitors arrive from unpredictable angles across the sky, frequently lingering for months or even years in solar glare zones that hinder clear viewing from our planet. When 3I Atlas was first spotted, it had already traversed the distant fringes of our solar system and was heading into its innermost solar swing. Orbital reconstructions indicate that this nomad entered our system as early as late 2024 or the start of 2025, steadily increasing in visibility as it neared the Sun and displayed initial comet-like traits. Such a late identification underscores a key hurdle in spotting these interstellar bodies. We detect them solely when they grow sufficiently luminous and align ideally for our telescopes to separate them from the starry backdrop. Forecasts position 3I Atlas's solar closest point, or perihelion, near October 29 or 30, 2025, at about 1:35 to 1:4 AU from the Sun. For context, this situates the object just within Mars's path, nearer to our star than any prior interstellar arrival has ventured. Its route will sweep 3I Atlas by Mars on October 3, 2025, at around 30 million kilometers. Though a remote pass by earthly measures, it's near enough for the advanced sensors on our Mars probes to possibly capture data during this pivotal sunward leg. The European Space Agency has outlined initial strategies to leverage its Mars-based orbiters for impromptu scans amid this rendezvous. From Earth's vantage, 3I Atlas stays at a comfortable remove during its transit. Its nearest pass to us happens at roughly 1:8 AU, or about 270 million kilometers. This separation guarantees the object presents no risk to our world, yet keeps it within reach of our premier observatories during optimal observation windows. Estimates of 3I Atlas's core size are still tentative, pointing to a fairly compact nucleus. Hubble Space Telescope images from July 21, 2025, limited its scale to maybe a few kilometers across, large enough to drive the noted comet features, yet dwarfed by the dazzling comets that have lit up our nights lately. These figures carry notable margins of error, given the difficulties in scrutinizing such remote, dim targets. The glow we observe stems from sunlight bouncing off dust and vapor in the encircling coma, rather than the core directly. Pinning down the true dimensions demands precise simulations of the nucleus's light-reflecting efficiency and the volume of ejected material from ice vaporizing mechanisms. The global effort to study 3I Atlas stands as one of the deepest investigations of an extrasolar guest to date. Hubble delivered sharp photos monitoring shifts in the coma's form and intensity across sessions. In August, the James Webb Space Telescope directed its infrared gaze at the body, uncovering molecular makeup details unattainable from terrestrial setups. Chile's Very Large Telescope supplied vital spectra, dissecting the object's radiance into spectral lines to pinpoint the exact compounds and elements illuminating its envelope. These findings highlight the distinctive chemical markers, including robust nickel signals without matching ions, striking cyanogen bands, and a prevalence of carbon dioxide, which have turned 3I Atlas into a focal point for researchers and enthusiasts alike. Various orbital observatories keep monitoring this interloper as it nears its October rendezvous, though opportunities for in-depth scrutiny from our planet are dwindling fast. The growing separation, coupled with tricky solar positioning, will soon render Earthbound viewing unfeasible, forcing reliance on insights from our Martian probes during the fleeting close pass. The worldwide collaboration underpinning this monitoring effort underscores the collaborative spirit of contemporary stargazing. Instruments in Chile capture the comet under southern skies, passing the baton to setups in Hawaii and the Canary Islands as our world spins the target into new sightlines. Orbital platforms ensure unbroken surveillance, sidestepping daytime interruptions and weather hurdles that hamper terrestrial telescopes. Yet the most captivating element of 3I Atlas's unveiling lies in how narrowly we escaped overlooking it. Its dim glow and awkward initial alignment allowed it to roam our cosmic backyard unseen for months or even years. Just how many comparable intruders have slipped by, never flaring brightly enough or aligning conveniently for our detection networks? Spotting these extrasolar travelers hinges on their dimensions, makeup, and path. Those failing to sprout significant tails could stay concealed until a tight solar skim, while ones incoming from select angles might lurk in the sun's blinding halo throughout their inner system jaunt. Projections indicate that for each such find, scores or hundreds could traverse undetected. 3i Atlas offers more than an isolated find. It's a window onto a potentially vast array of stellar nomads routinely threading our local space. As October 2025 unfolds, 3i Atlas presses on toward its closest solar point, now discernible to skilled skywatchers using basic scopes. Its verdant haze stands out as a signature in the fall heavens, signaling how our system acts as a hub for voyagers from afar. Prior to fading into solar dazzle, Mars claims prime viewing for any enigmas this guest bears. The puzzle persists. Do our tools, whether Martian or terrestrial, possess the finesse to tease apart the alien from the astonishing in our narrowing observation slot for this extraordinary spacefarer? Part 7. Peculiar Hues and Peculiar Composition. The cosmos sketches its tales across light spectra, and 3i Atlas has been crafting a verdant opus since its spotting. As this extrasolar guest draws nearer to our star, its core warms, unleashing long frozen vapors trapped in ices across eons. But the spectrum unfolding from this stellar creator diverges from the palettes typical of our system's native bodies. The emerald tint, enchanting global viewers, stems from intricate chemical and physical dances in the near void encircling the core. When molecular structures get energized by solar UV rays or impacts, they glow at precise frequencies shaped by their atomic electron setups. For that green radiance, prime suspects include C2 molecules and CN radicals, both shining vividly under solar illumination. Live science media reports on this intriguing event have delved into the primary suspects behind the comet's striking green hue, highlighting that although diatomic carbon continues to stand out as the prime culprit according to previous comet studies, the exact molecular compound causing 3i Atlas's distinctive tint hasn't been conclusively identified via detailed spectral analysis. This difference is crucial since various molecules offer unique insights into the environmental factors that shaped and developed this interstellar guest. Cyanogen, formed from carbon and nitrogen, counts among the deadliest compounds in chemical science. However, it emits a ghostly luminescence when released into the emptiness of space. Detecting it in comet spectra yields hints regarding the organic reactions that took place in the star-forming region from which 3i Atlas emerged. The levels of cyanogen compared to other carbon-containing molecules can uncover information on heat levels, atmospheric pressures, and reactions from eons past near a far-off sun. Still, this emerald radiance is merely the most noticeable part of a far richer chemical narrative. When the Very Large Telescope in Chile directed its advanced spectrometers at 3i Atlas, it uncovered molecular signatures that question our preconceptions about the conduct of objects from beyond our solar system. Spotting strong nickel emission features without the usual accompanying iron traces poses a compositional riddle, prompting scientists to rethink their ideas on comet makeup. On Earth and in typical meteorites, nickel and iron coexist in proportions mirroring the stellar fusion that created them in ancient stars. The elemental distribution etched in the periodic table implies they ought to show up in consistent amounts across the universe. Yet 3i Atlas appears to defy this core principle of astrophysical chemistry. VLT data gathered as the comet neared showed robust nickel signals at 588 nanometers, a vivid green peak that emerges sharply from the intricate backdrop of gaseous emissions. Those precise tools also hunted for iron signals at similar lengths, but detected virtually none. The detection thresholds were tight enough that standard cosmic ratios would have made iron straightforward to spot. Various hypotheses have surfaced to explain this oddity. Organic molecules rich in nickel, resilient in the frigid void between stars, could break down from sunlight exposure, favoring the vaporization of nickel over other elements. Long-term exposure to space conditions might reshape outer layers, influencing which substances emerge from evaporating ices. Overall observations from numerous studies depict 3I Atlas as an outsider forged under conditions vastly unlike those of bodies from our solar neighborhood. James Webb Space Telescope scans with the IR-SPEC tool showed a makeup led by carbon dioxide, while water ice contributed little in the initial stages of outgassing. Such heavy reliance on CO2 suggests origins in a chillier, more abundant volatile zone than the area birthing Earth and its rocky siblings. Planetary disks around other stars follow unique thermal gradients, which might produce comets with chemistries alien to our Oort cloud or Kuiper belt. The European Space Agency's review of this infrared data points out that the reduced water-to-CO2 proportion at great distances from the Sun aligns with standard startup patterns, as the easiest to vaporize ices turn to gas before others as the comet warms. As 3I Atlas draws nearer to the Sun, the proportion of water vapor in its total gas output is expected to rise, since the less stable ices will start sublimating at higher temperatures. The output levels of various molecular components offer further insights into the object's composition. With 3 Atlas getting closer to the Sun, the generation of water vapor, carbon dioxide, cyanogen, and additional compounds ramps up steadily as the distance from the Sun shrinks. These output profiles align with typical behaviors for sublimating ices, offering solid proof that the phenomena we see stem from ordinary physical mechanisms, not manufactured sources. Still, amid this reliable pattern, minor irregularities linger that continue to captivate scientists. The proportions among the production rates of these molecules don't quite fit the predictions drawn from comets in our solar system. Fluctuations in brightness reveal indications of uneven makeup on the nucleus's surface or targeted gas releases from underlying activities that scientists still don't fully grasp. The network of amateur astronomers has been vital in recording these shifts in chemistry across time. Sharp images from skilled watchers globally deliver ongoing monitoring that outpaces what pro-telescopes can achieve, given their tight schedules and other demands. Such data capture alterations in the coma's hue, tail formation, and general luminosity, enhancing the in-depth spectral examinations from leading facilities. Online platforms have heightened focus on some of these chemical enigmas, at times turning early findings into overhyped assertions that go beyond the evidence. The detection of nickel-absent iron has led certain interpreters to speculate about industrial activities or production marks, even though viable natural accounts exist for it. Officials at NASA maintain that the data so far points to a genuine cometary interloper, though one featuring distinctive traits that aren't entirely without precedent. Experts from the agency point out that such chemical quirks make sense for items originating near other stars, where varying conditions in heat, density, and element mixes might yield structures alien to our local system. Drawing a line between the unusual and the implausible stays key to making sense of these findings. Chemistry that's odd yet accountable via established physics stands apart from that which could hint at engineered beginnings. 3I Atlas shows clear signs of the former, but if these traits veer into the latter category is still up for scientific discussion. Looking back at past cases gives valuable insight into these chemical quirks. Comet 2I Borisov, the prior interstellar object examined closely, had its share of chemical surprises that first baffled experts. Its ratio of carbon monoxide to water strayed far from norms in solar system comets. But thorough studies showed these variances could arise from its birth in the chillier fringes of its home star system. Analyses of 3I Atlas cover potential chemical routes that might generate the noted nickel traces without resorting to far-fetched ideas. Compounds like nickel carbonyl arising from interactions between nickel-rich dust particles and carbon monoxide in the frigid space between stars might account for why nickel emerges more readily than iron under the sun's warmth. As October 2025 advances and 3I Atlas presses onto perihelion, chances for in-depth chemical scrutiny are fading. The very solar warmth that sparks. The most captivating chemical reactions also place the comet in progressively difficult positions for observation from ground-based telescopes on Earth. What if the activation we witness isn't merely chemistry stirring under the sun's influence, but rather programmed sequences initiating as part of a more profound blueprint? The molecules themselves offer no clues about their true beginnings. They merely shine with the exact quantum mechanical accuracy that dictates all matter, be it born of nature or engineered by an intelligence beyond our current grasp. Part 8 covers the Mars flyby. October 3, 2025, signals a stellar rendezvous crafted over millions of years. On that day, 3IA Atlas will glide by Mars at roughly 30 million kilometers away, near enough for the planet's array of robotic probes to aim their sensors at this visitor from beyond our solar system, and possibly capture the sharpest data ever on an object hailing from another star. In planetary science terms, 30 million kilometers doesn't count as a near miss. That span equates to about 5 times the Earth-Moon distance, or roughly 1/5 of an astronomical unit. Yet, for interstellar travelers on hyperbolic paths moving at tens of kilometers per second, it offers a remarkable chance for in-depth examination during a key stage of the comet's journey toward the Sun. The European Space Agency has outlined initial strategies to synchronize observations via several Mars-orbiting missions during this short window. The ExoMars Trace Gas Orbiter, built to probe the Martian atmosphere, features spectrometers suited for dissecting the chemical makeup of 3IA Atlas's growing coma. Mars Express, now well into its 3rd decade circling the red world, adds imaging tools and spectroscopic gear that might enhance our insights into this extraterrestrial guest. NASA's Mars Reconnaissance Orbiter, fitted with the powerful HiRISE camera system, holds the most promising potential for scrutiny. Though the comet lies too far for resolving surface details, HiRISE's superior sensitivity and clarity might uncover features in the coma structure, dust patterns, and tail shapes that escape detection by Earth-bound scopes hampered by our atmosphere. The viewing setup during the Mars Pass grants benefits no terrestrial sight can match. Mars sits at a unique vantage relative to the Sun-comet alignment, which could expose parts of the coma and tail hidden from our planet-bound views. Free from atmospheric distortion, there's no blurring from seeing conditions or absorption by air layers, paving the way for crisper pictures and more precise photometric readings. Still, major hurdles shadow these efforts. Mars satellites were engineered mainly to examine the surface beneath them, not remote deep space targets. Their orientation mechanisms, data links, and storage setups prioritize those core tasks, demanding meticulous planning to swivel toward objects millions of kilometers off while upholding main operations. The research aims from these Mars platforms center on profiling elements of 3IA Atlas that ground studies leave unclear. Fine-tuned images might map dust particle sizes in the coma by studying sunlight scattering across various phase angles. Spectral scans could pin down proportions of molecular types, especially amid vigorous outgassing as the comet nears the Sun. The ion tail's form emerges as yet another promising area. This comet serves as a prime objective for observations conducted from Mars. The interplay of solar wind with the ionized vapors in the comet's surrounding atmosphere forms unique tail formations that follow the orientation of the nearby magnetic field. Observing from Mars's distinctive perspective, these characteristics of the ion tail could uncover insights into the comet's rates of gas emission and the surrounding space conditions, details unattainable from Earth's viewpoint. The schedule of the Mars close approach heightens the need for prompt observational strategies. 3I Atlas is set to endure progressively stronger solar radiation as it nears its perihelion in late October, which could spark the most spectacular release of gases during its journey across the solar system. The flyby by Mars happens right when this outgassing is ramping up to its maximum, providing a rare glimpse into comet dynamics that might not occur again for decades or even centuries. Yet, inherent constraints limit the capabilities of even the most advanced instruments on Mars. At a distance of 30 million kilometers, 3I Atlas will show up merely as a tiny dot in the views of most cameras on the circling probes. In-depth analyses of the core's shape or accurate charting of the atmosphere's extent exceed the capabilities of existing Mars satellites. Delays in communications from Earth to Mars add further hurdles to coordinating live observations. Signals via radio require 4 to 24 minutes for the trip between the worlds, varying with their orbital alignments. Consequently, viewing protocols have to be set up beforehand and sent to the probe's storage, allowing only minimal tweaks. Adjustments relying on immediate shifts in the comet's actions prove challenging. Dust storms on Mars introduce an additional uncertain element that might impair data clarity. Although large-scale global storms are rare, smaller local or regional ones can obscure sights and interfere with delicate equipment. Planners for the mission need to weigh the push for ideal timing against the erratic weather on Mars, which risks undermining the integrity of the gathered information. The schedule for sending data back introduces yet more intricacies to the viewing efforts. Satellites around Mars usually transmit their acquired information to Earth in planned contact slots, which might not sync well with the short flyby window. Certain key findings could take days or weeks to arrive post-event, restricting chances to arrange subsequent research or distribute initial discoveries to the worldwide community of astronomers. Even with these obstacles, the Mars Pass offers the top chance to examine an object from beyond our solar system at its height of activity. Telescopes on Earth will shortly be unable to follow 3I Atlas as it dips into the sun's blinding light, positioning these Mars views as possibly the final sharp look at it before it reappears from solar conjunction months hence, assuming it does. The insights gained from these views might deliver vital validations for rival hypotheses on 3I Atlas's origins. Standard comets facing heat treatment close to the sun ought to exhibit foreseeable sequences of dust and vapor ejection, detectable via shifts in the atmosphere's luminosity and tail shapes. Notable differences from such anticipated behaviors could point to unconventional interpretations of the intruder's actions. That said, it's essential to hold measured hopes regarding the scope of revelations from these views. The Mars encounter won't feature any direct interaction or near pass. The intruder will stay millions of kilometers distant the whole time. No material will be gathered, no traits of the surface will come into focus, and no specifics on inner makeup will be secured. This viewing initiative also acts as a demonstration for upcoming probes of interstellar objects. Methods refined and validated in this process. The 3I Atlas Mars. Flyby might shape observation plans for upcoming explorers, possibly fostering more advanced and unified global initiatives to examine these uncommon interstellar drifters. Contingency preparations account for potential issues like equipment malfunctions, signal disruptions, or suboptimal sighting angles that could restrict or nullify valuable insights from the rendezvous. Alternative viewing methods relying on ground telescopes offer partial safeguards, yet they face growing interference from solar brightness and earthly atmospheric constraints as the flyby draws near. The Mars rendezvous schedule squeezes the prime scientific observation phase into only a handful of hours or days near the point of nearest passage. In this narrow time frame, our automated probes circling the crimson world will direct their sensors at an intruder from beyond our star system, striving to record any enigmas it unveils while traversing our stellar domain. If Mars could tune into the radio waves during those pivotal moments, what tales might it pick up amid the cosmic noise? The devices will monitor with mechanical endurance and the inquisitiveness of their designers, aiming to unravel any signals embedded in the glow of this stellar nomad. Yet before that, the interloper needs to fulfill its meeting with our solar system's fourth world, bearing its concealed wonders beyond the vigilant gaze of our Martian outposts toward its final path, obscured by the intense light of our sun. Part 9. SWNR2, the New Giant. Although 3I Atlas drew fascination as an unusual guest from deep space, a different celestial voyager was subtly gearing up to dominate the spectacle. Comet C225R2, more commonly called Swan R2, following its detection in solar and heliospheric observatory records, rose from the outer reaches of our own solar system to deliver one of the grandest comet shows observable from our planet in recent times. The tale of its finding stems from the steadfast commitment of hobbyist stargazer Vladimir Bazougi, who devoted countless hours to scrutinizing Swan sensor images in search of subtle indicators of fresh comets concealed within the Sun's radiance. On September 11, 2025, his diligence yielded results when he spotted an irregular glow in the readings, which was quickly verified as an undiscovered comet nearing its perihelion with the Sun. The SWAN instrument solar wind anisotropies on the SOHO satellite acts as an improbable seeker of comets, even though its main purpose is to investigate solar wind dynamics with the space between planets. Through charting the spread of hydrogen particles produced as water vapor disintegrates under solar UV rays, SWAN identifies cometary behaviors that evade standard optical instruments, especially for bodies positioned too near the Sun for secure terrestrial viewing. SWAN R2's appearance after solar conjunction highlights a key hurdle in spotting comets. Bodies on extended orbital paths frequently linger for months as they near the Sun from angles that keep them at minimal separation from our star as viewed from Earth. The whole Schick effect, honoring the Austrian skywatcher who initially outlined it, clarifies why numerous dazzling comets materialize abruptly overhead, already vibrant and operational. The comet's formal label as C-225R2 adheres to the International Astronomical Union's standardized nomenclature. The C signifies a long-period comet, probably hailing from the remote Oort cloud encircling our solar system. The year 2025 denotes its detection year, whereas R2 shows it as the second comet found in the latter half of September. By mid-September 2025, SWAN R2 had attained visibility to the unaided eye for those in clear, dark locations, gleaming at roughly 6th magnitude. This marks the limit at which celestial bodies can be seen by the naked eye in perfect viewing scenarios. Yet, in contrast to most comets that reach maximum luminosity before dimming, this interstellar guest kept increasing in brilliance after swinging past the Sun and heading for its nearest pass by our planet. On September 16th, the astronomy picture of the day showcased SWAN R2 as a freshly identified comet detectable via binoculars, emphasizing its swift surge in glow and the impressive tail formation, turning it into a top pick for astrophotographers around the globe. Its location close to the luminous star speaker within the Virgo constellation offered a handy guide for hobbyist skywatchers trying to spot it amid the evening dusk. Accounts from seasoned comet spotters started recording tail extensions reaching as much as 2 degrees in the heavens, about fourfold the full moon's visible width. Although these estimates are rough, given the personal judgments in eyeballing comets and the methods applied in photo editing software, they indicate a tail extending across millions of kilometers in actual size. The path of SWAN R2 reveals its origins from the distant edges of our solar system. Differing from 3 Atlas in its hyperbolic path from beyond our stars, SWAN R2 traces a highly stretched elliptical orbit that takes it from the icy zones past Neptune's path to just 0.5 astronomical units from the Sun. Such a voyage spans dozens or hundreds of years, with the comet staying dormant and iced over until the Sun's warmth ignited the dazzling spectacle we're witnessing now. Its perihelion took place on September 12, 2025, as SWAN R2 came within about 0.5 astronomical units of the Sun, half the Earth-Sun separation. That near-solar brush exposed the comet to fierce temperatures, melting its outer ices and unleashing the particles and vapors forming the evident coma and tail features. SWAN R2's minimal distance to Earth is expected on October 21, 2025, skimming by at 0.27 astronomical units or around 40 million kilometers. This setup offers prime observation angles, positioning SWAN R2 ideally for close scrutiny right as 3I Atlas nears its own perihelion. Recent light assessments rate SWAN R2 at magnitude 6 to 7 in mid-September, readily observable with binoculars and edging toward unaided sight for those in dark, clear sights. Ongoing intensification hints that it could hit magnitude 4 or 5 near Earth's flyby, possibly ranking among 2025's most radiant comets. Southern sky regions offer the best chances to view SWAN R2 in the evening hours. Northern viewers, meanwhile, might catch it hugging the western horizon post-sunset. The The comet's alignment with the ecliptic and its path across Earth's view shift the sight lines, influencing how well it's seen over its visibility period. Global amateur astro groups have rallied to track SWAN R2's evolution, building an ongoing data repository that supports expert research efforts. Striking photos from veteran comet imagers uncover fine nuances in the tail, such as possible disconnects where solar wind effects briefly detach sections of the ion tail from the core. Still, key doubts linger about SWAN R2's orbit details, owing to the limited tracking span since detection. Outgassing on comets generates extra pushes beyond gravity, quietly tweaking their courses and complicating accurate forecasts far ahead. Until additional data from observations is gathered, the Minor Planet Center keeps updating its orbital calculations as fresh astrometric data streams in from global observatories. Such data will ultimately clarify if SWAN R2 traces a bounded elliptical path that could return it to the inner solar system someday, or if gravitational influences during its current transit will hurl it forever into the void of interstellar space. Risk evaluations show no danger to our planet from SWAN R2's present path, with a minimum approach of 0. 27 astronomical units, it ensures a safe buffer while opening up prime chances for in-depth examination of this interloper from the solar system's fringes. Routine vigilance measures persist in tracking the comet's course for any unforeseen shifts that could alter these forecasts. Its swift evolution and dazzling display have turned it into a prime pick for community engagement and learning initiatives. Around the world, stargazing groups and planetariums are weaving SWAN R2 into their events, leveraging its prominence to inform crowds on how comets form, the layout of our solar system, and the lively forces molding our celestial surroundings. Leading observatories are now adding SWAN R2 to their observation schedules for spectral analysis and photometric examinations. Although the bulk of observing slots is still devoted to 3I Atlas owing to its bizarre origins beyond our stars, SWAN R2 presents key prospects to probe the makeup and dynamics of bodies hailing from the distant edges of our own solar system. SWAN R2's arrival, occurring almost at the same time as 3I Atlas's journey into the inner solar system, opens a rare window for side-by-side analyses. These two distinct kinds of celestial wanderers, one from afar in the stars, the other from our own Oort cloud face, comparable stresses and solar warmth, enabling scientists to explore how an object's birthplace influences its cometary traits. If 3I Atlas acts as a lone explorer scouting our stellar locale, then why does SWAN R2 show up like a massive urban messenger signaling events of much greater scale? Cosmic alignments this handy for contrast rarely occur, positioning October 2025 as a pivotal time that could transform our grasp of the entities drifting amid and inside star systems. Part 10. Delving into technical hypotheses on propulsion, defenses, and paths. In the domain of conjectural stargazing, the boundary between the bizarre and the constructed frequently fades, as odd sightings spark bold ideas on the potentials of a cosmos teeming with undiscovered minds. 3I Atlas and SWAN R2 stand as current examples that, though accountable via ordinary cosmic workings, also prompt thoughts on bolder possibilities, even if just as mental exercises in the science of guided travel and managed power output. Start with the topic of drive systems. Typical comets adhere to routes shaped solely by gravity's pull, their routes across the void governed by the inverse square rule, and the starting setups of their birth or expulsion from remote star clusters. Any real engine would betray its presence via detectable strays from these anticipated tracks, steady thrust directions, orientation shifts, or path adjustments that defy the rules of unpowered flight. A focused ion thruster, which works by spewing charged particles at extreme speeds, would leave detectable traces in the object's path and its light emissions. The jet of waste would shine at specific colors based on the makeup and heat of the released stuff. Even more crucially, the push direction would induce noticeable alterations in the key elements of its orbit. Deviations that build up gradually and result in obvious breaches of Keplerian orbits are absent in 3I Atlas. It exhibits a hyperbolic path that aligns precisely with the anticipated route for a body not gravitationally tied to our Sun, featuring luminosity and spectral shifts that align reliably as it draws nearer to the Sun. The venting detected by our finest detectors seems wholly in line with ordinary sublimation triggered by solar warmth. Nevertheless, the exactness of its schedule reaching the neighborhoods of Mars and Earth in a tight time frame that overlaps with Swan R2's nearest passes defies probabilistic norms, leaving room for speculative theories. Should deliberate synchronization, not mere chance, account for this overlap, it would demand drive mechanisms functioning so discreetly as to evade detection from today's monitoring techniques. Another domain where organic events could conceal engineered operations is electromagnetic protection. Comets routinely form plasma layers. Solar wind engages with charged vapors in their growing comas. Such engagements generate intricate magnetic configurations that redirect charged matter and form the typical anti-solar orientation of ion streams. A deliberate electromagnetic setup could closely mimic these organic plasma exchanges, varying solely in the level of guidance and focus it applies to the nearby ionized surroundings. The crucial difference would emerge in spotting field patterns lacking any clear organic role magnetic arrangements fine-tuned for signaling, power harvesting, or radiation defense instead of basic solar wind repulsion. Present data show ion streams acting just as predicted from standard comet solar wind dynamics. The James Webb Space Telescope, along with earthbound spectrometers, pick up no irregular electromagnetic traces, no unified radio signals, no signs of directed field creation exceeding the innate outputs of solar wind effects on lively comets. The dynamics of planned scouting paths would necessitate cycles of recurring visits or organized sweeps that set engineered courses apart from the haphazard meetings typical of innate interstellar drifters. Extended period comets originating from our own Oort cloud might pose as one-off sightings, despite tracing bounded oval paths. As their cycles frequently surpass the span of human records, genuine scouting patterns would ultimately surface via repeated showings at foreseeable gaps, joint arrivals of various bodies, or path adjustments aimed at tactical goals over mere pull of gravity. The trio of verified interstellar intruders spotted since 2017 are Norkai Oumuamua, 2I Borisov, and now 3I Atlas display no hints of arranged intervals or joint operations. Avi's reply to the signal idea offers an intriguing mental exercise on how our radio spills into the cosmos could spark automatic replies from inactive surveillance networks spread across our nearby stellar region. This notion could account for the seeming link in timing between our tech progress and the influx of odd arrivals. Still, NASA and ESA insist that existing sighting records align with innate accounts, even amid their quirky traits. The organizations stress that bold assertions demand robust proof, and the molecular markers, path physics, and material actions seen in both 3I Atlas and Swan R2 fit inside the spectrum of innate cometary events, though toward the rarer extreme. The finding of nickel-absent iron in 3I Atlas's spectrum demonstrates how odd compositions might get explained. Examining the phenomena through both organic and engineered perspectives reveals key insights. Manufacturing techniques can isolate specific elements or isotopes, yielding unique markers in the output gases or waste flows. Yet, the VT examination delves deeply into organic mechanisms, including nickel carbonate reactions, impacts from cosmic erosion, and targeted vaporization effects that might generate comparable chemical traces absent any engineered causes. Shifts in hue and sudden illumination patterns highlight yet another domain where organic and constructed interpretations vie for explanation. Comets frequently exhibit irregular intensification patterns as various volatile compounds hit their evaporation points at varying distances from the Sun. Such patterns mimic distinct ignition moments that could imply drive mechanisms activating, though they actually stem from the dynamics of frozen vapors turning to gas in empty space. Separating organic venting from engineered expulsion demands scrutiny of force directions, speed gain curves, and power allocations that surpass what haphazard evaporation could achieve. Existing data indicate luminosity and color spectrum alterations that align precisely with the anticipated responses of evaporating frosts exposed to rising sunlight intensity. Potential indicators of true design would emerge via multiple detection methods. Steady propulsive force would build up into observable path deviations over periods. Orientation mechanisms would cause rhythmic fluctuations in luminosity or color traits as varied facets or parts turn toward or from the sun. Unified radio wave outputs would contrast sharply with the ambient space noise. Global collaborative surveillance initiatives have hunted for precisely these irregular traces, employing radio dishes, radar arrays, and precise light-capturing devices. Facilities like the Very Large Array, successors to Arecibo, and other key radio sites have performed thorough scans for constructed signals from extraterrestrial probes. No unified broadcasts, no patterned radio outputs, no signs of functioning circuits have surfaced. Radar scans by various installations have likewise yielded empty outcomes. Although the vast separations pose detection hurdles even for the strongest planetary radar setups, the absence of robust radar echoes aligns with organic comet exteriors made of sparse frost and particle blends, not metallic or mirror-like built forms. Heat-sensing scans offer further evaluation of engineered versus organic sources. Probes or fabricated items usually present warmth patterns distinct from unaltered objects, owing to onboard heat generators, temperature controls, or unusual substances. Both 3I Atlas and SWAN-R exhibit heat radiation curves matching sunlight, warming of organic frost and particle combos. The power demands suggested by diverse engineered hypotheses also challenge plausibility under close numerical review. Interstellar voyages demand massive energy outlays, be it for speed building, habitat maintenance, or signaling over cosmic spans. Items equipped for such treks would probably reveal traces of sophisticated power setups that our data notably lack. Response escalation guidelines operate within the Global Astronomy Network for handling truly irregular findings. Should various separate observatories spot definitive proof of constructed markers, organized waves, unexplainable path shifts, or implausible material blends, joint pursuit operations would rally assets from NASA, ESA, and other cosmic bodies to launch thorough probes. These guidelines have not been triggered for either 3I Atlas or SWAN-R2 shows that, regardless of their odd features, these items still fit into the realm of natural events as recognized by conventional astronomical knowledge. Experts generally lean toward unconventional yet earthly causes for the traits they've shown. That said, the lack of any spotted man-made signals doesn't fully confirm they're purely natural, especially if we're talking about tech from advanced societies that evades our present tools. Such groups could use drive mechanisms, signaling techniques, or building materials that generate traces we simply can't pick up or make sense of with our current know-how. This gap in our understanding, our failure to rule out engineered elements for sure leaves room for ongoing debates about possible tech-based views. The divide between detectable realities and potential unseen possibilities opens the door to ideas that can't be tested with today's equipment. The draw of tech-oriented theories taps into our innate urge to spot intent and smarts in cosmic events that could just be random flukes. The exact moments when both intruders showed up, their bizarre traits, and their overlap in our solar neighborhood amid humanity's tech boom, form storylines that our brains, wired for patterns, see as possibly significant. Crunching numbers on how often star-hopping visitors arrive points to the recent bunch of weird ones likely stemming from better spotting biases, not a real uptick in actual drop-ins. In the last 10 years, our spotting tech has leaped forward, so we're bound to catch things that zipped by unnoticed back in the day. Since 2017, we've nailed down 3 such cosmic drifters, 1I Oumuamua, 2I Borisov, and 3I Atlas, all of which baffled scientists at first but eventually bowed to straightforward natural accounts after close scrutiny. This history implies that quirky aspects don't automatically signal alien tech, even if they push the limits of our models. Models run on computers for paths of star-crossing bodies suggest our solar setup gets natural guests at paces that match what we've seen lately, based on solid guesses about how many tossed-out chunks float in our nearby galactic patch. The schedules and quirks of these fresh arrivals land squarely in the range we'd predict for everyday interstellar nomads. Still, there's always the chance that a share of these spotted wanderers could be tech so refined it blends seamlessly with nature, whether on purpose or just because cutting-edge design works hand in glove with physics. We'd have no way to tell it apart from rocks with our tools right now. The real showdown between these rival ideas might unfold in October's sun grazes, when both will face their fiercest bake and could expose hidden sides from their milder inbound legs. Should engineered setups be involved, the crush of closest solar flyby might spark reactions or breakdowns that set them apart from simple stones. Earth scopes will go dark on watching either during their tightest sun hugs, leaving a key window blind right when science needs eyes most. This coverage hole suggests the strongest clues for or against tech angles could pop up exactly when we're looking away. Mars side watches. The 3 IA Atlas flybys on October 3rd offer our prime opportunity to keep tabs on things during this vital period, even if the shortcomings of current Mars satellites limit what we can spot, no matter the circumstances. The gear on these probes was built for studying planets, not picking up odd happenings from fleeting interstellar travelers. Spotting real devices concealed within these space drifters would demand viewing tools and study methods that stretch far beyond today's standard astronomy. The line between highly evolved tech and ordinary cosmic events could turn out to be far trickier to spot than our existing scientific models can handle with confidence. What this examination really raises isn't if we've uncovered signs of engineered intruders, but if we'd even identify them, should they appear in ways that go beyond our notions of how tech might evolve over vast interstellar spans and eons of use. If a device were posing as a comet, what exactly would show up in our scopes? Maybe just what we're observing right now. These enigmas test our grasp of reality while staying barely believable as natural, dodging the high bar of proof needed for bold assertions. The cosmos guards its mysteries closely, sharing them solely with watchers clever enough to pose the proper inquiries and steady enough to admit that certain truths might stay out of grasp for now. Part 11. Shared Purpose. What might unite them? In the grand arena of the cosmos, chance happenings morph into plots and schedules shift to scripted moves whenever our brains seek order amid the stellar disorder encircling our tiny planet. Two intruders showing up mere weeks apart, showing matching traits and paths that meet at our star in the very same tight time frame, start seeming less like fluke meetings and more like synced pieces of a grander scheme. Letting fancy bridge the spots where facts go quiet, picture Swan R2 as a roaming supply base, with 3 IA Atlas acting as a swift survey drone. In such a hypothetical setup, the huge comet and its vast trail aren't some simple frozen chunk, but a clever supply hub, its seeming instability hiding managed supplies and signaling setups. The compact, agile 3i Atlas could play the role of a sharp-eyed explorer, collecting details on our solar setup's features and relaying them to the bigger outpost. This base and explorer setup could account for various baffling traits in how they have acted. 3. I-Atlas's exact schedule and path might show intentional steering to set points where Swan R2 sits ready for info handover, supply swaps, or repair aid. The odd chemical traces we chalk up to weird venting could in truth be deliberate releases, propellant shifts, air handling, or waste from tech running hot under intense heat. Other views propose these are plain rocks, hijacked by an old surveillance web dotted across our nearby stellar zone. Instead of custom ships, they might be seized asteroids and comets, their outsides or insides tweaked to host self-running gear that kicks in under set triggers, like picking up radio waves from budding advanced societies. This ride-along idea would clarify why both arrivals show features that hover right on the edge of what we consider ordinary natural events. An advanced society capable of setting up vast networks to watch over stars would probably opt for secrecy rather than visibility, employing disguises and imitation to steer clear of provoking protective reactions from other life forms they come across. Transforming everyday cosmic bodies into tech bases offers ideal concealment, letting man-made setups blend seamlessly into the vast array of asteroids and frozen chunks drifting through the void between stars. Our star could function as far more than a mere anchor for gravity in these activities. Sunlight delivers a boundless supply of power for devices built to capture energy from light waves, and the stream of charged particles from the sun generates a lively charged gas setting that might enable strange physical effects we haven't grasped yet. Flows of ions rushing out from the sun could act as both a way to send signals and a fuel provider for inventions based on concepts still unknown to us. Ideas about watchful arrays imagine clusters of outposts placed strategically across star systems, keeping tabs on how worlds evolve and how tech-savvy beings arise. The pull of the sun's gravity forms handy gathering spots where data from far-off detectors might get compiled, analyzed, and sent onward to remote oversight posts. The gathering in our solar system during October 2025 could just be a standard effort to gather and pass along information. The idea of a pursuer and gatherer pairing gives a darker spin on why these moments line up so neatly. Should 3I Atlas stand for a hunting mechanism aimed at spotting and eliminating budding dangers, Swan R2 could then function as a mining outpost built to handle any resources the pursuer brings in. The contrast in size between the agile explorer and the huge handler would highlight their distinct parts in a broader effort that sees our solar system as a potential prize or peril. Visions from this imaginative setup depict the tiny messenger twisting closer to its meeting point as the bigger structure deploys gathering tools and handling gear, ready for any substances or intel the explorer brings. The comet-like behavior we spot could be hiding much more deliberate actions, like gathering power, reshaping matter, or building short-term setups to aid prolonged activities near us. Such ideas dwell purely in the world of speculation, backed by no solid sightings, yet they're gripping enough to draw people's interest because they give shape to occurrences that might otherwise feel haphazard and pointless. Our brains resist pure chance, favoring accounts that suggest purpose and planning no matter how wild the jumps from what we actually know. The clash between random alignment and deliberate arrangement touches on bigger debates about what smarts look like across the cosmos and how well we can spot it in strange guises. If highly evolved societies commonly use tech that echoes natural ways, how could we tell real cosmic happenings from clever fake ones that fool us? The bunching of incidents in October offers a solid timeline to build these imaginative tales around. Swan R2's closest swing by the Sun on September 12th, 3I Atlas's flyby of Mars on October 3rd, 3I Atlas's perihelion on October 29th, and Swan R2's nearest pass to Earth on October 21st form a chain of positions in space and time that might signal mere stellar luck or a meticulously arranged performance. Stories from ancient human traditions offer patterns for making sense of paired civilizations across the globe, have long viewed incoming celestial bodies as signs or precursors to profound shifts. Every society on our planet boasts myths about skyborne intruders that heralded the shift from one era to another. Luminous displays that foreshadowed the ascent of great realms, the collapse of ruling houses, or the dawn of fresh insights and authority. Perhaps 3I Atlas and Swan represent a contemporary echo of these timeless motifs. The persistent query woven through our inquiry, whether it's a comet, a bastion, or a response to a signal we unknowingly dispatched, gains fresh layers when considering these dual arrivals instead of isolated oddities. If one embodies the dispatch and the other the retort, their alignment could signal the finale of a dialogue initiated when our broadcast signals first seeped into the cosmos generations back. Yet, at this juncture in our tale, viewer direction proves essential. We've ventured beyond the boundary of verifiable evidence, forsaking the stability of empirical records for the riskier seas of conjecture and potential. The core details anchoring our probe, the sequence in October, the molecular traces, the paths in orbit, still bolster everyday origins, all while fueling bolder readings. The notion of a joint endeavor presumes synergy without confirmation, intent where happenstance offers a straightforward account, and sentience where organic mechanisms suffice as rationales. Such notions mirror our innate drive for significance and order as profoundly as they highlight authentic enigmas in the conduct of these extrasolar wanderers. Still, we can't wholly rule out that certain pinnacle technologies could blend so seamlessly with innate phenomena, either intentionally or as a byproduct of designs that harmonize with physics' core principles. Spotting such feats would demand tools and interpretive models surpassing today's expertise. The true trial for these collaborative intent theories might unfold amid the impending solar flybys, as both entities endure their fiercest thermal trials and possibly unveil traits concealed in their milder inbound legs. Should synergy link these forms, it could surface amid the strain and prospects of closest solar approach when power demands and signaling needs hit their zenith. The blind spot from the sun's brilliance in these pivotal intervals implies that the clearest proof either way for synchronized actions could arise just when our detectors go dark. We might exit the October hush armed with sharper insights into routine comet dynamics, or we could face clues that upend our bedrock views on what traverses the void amid the stars. If they pursue a common goal, what objective calls for both a precision tool and an industrial hub? The resolution could etch itself in solar flames over the obscured days to come as these stellar sojourners perform their last visible maneuvers before fading into the annals of recollection and theory. Part 12. The Relay Hypothesis, a Stellar Information Handover. In the domain of conjectural stargazing, where fancy intersects with science, scant ideas evoke a feeling of interstellar intent as vividly as the relay concept. The premise that 3i Atlas acts as an info bearer, with Swan R2 as a hub for computation and relay, both homing in on our star to finalize a data swap prepared over years or even decades. Envision 3i Atlas as the herald, journeying from deep space laden with compacted records of sightings amassed over its extended trek across our neighborhood in the galaxy. In the vicinity, this object's compact dimensions and agile path indicate a design focused on velocity and agility over large-scale data retention. Nevertheless, even a compact entity might hold immense quantities of data if utilizing cutting-edge encoding methods in storage. The peculiar chemical traces detected could signify deliberate data encoding rather than mere natural venting. Data inscription occurs onto tangible mediums as the messenger nears its planned meeting point. Swan R2, originating from the fringes of our solar system, exhibits the contrasting characteristics of a hub built for computation and signal forwarding. Its enormous proportions and striking tail formation may conceal advanced gathering mechanisms and broadcasting setups tailored for the harsh settings around stars. The seeming comet-like behavior could obscure targeted energy projections, plasma control devices, or unconventional signaling tools that work by altering solar wind patterns. The sun emerges as the pivotal third component in this imagined relay setup. Our central star stands as the dominant power generator across vast astronomical spans, able to energize mechanisms that portable sources couldn't sustain independently. Yet, the sun delivers beyond mere power output. It generates a distinctive setting where effects like gravitational bending, magnetic engagements, and plasma movements could support signaling methods grounded in concepts surpassing our present knowledge. Gravitational bending offers a viable approach for far-reaching exchanges via star-sized setups. Einstein's theory of general relativity foresees that hefty bodies such as stars can concentrate electromagnetic waves, forming inherent magnifiers able to pick up transmissions from immense ranges. A highly evolved society could deploy forwarding nodes at key gravitational convergence spots across the galaxy, leveraging stars to boost networks bridging vast cosmic gaps. The charged particle layer encircling our sun opens up further avenues for novel physical uses. The solar breeze transports ionized bits across the solar realm, forming conductive pathways and magnetic frameworks ripe for alteration by superior tech. Picture setups that embed data straight into plasma streams, imprinting signals within the magnetic patterns. These patterns rush by worlds and out toward the stars. Pictorial depictions of this imagined data transfer evoke vast manufacturing efforts hidden behind everyday cosmic events. SWAN R2 deploys intake panels posing as nebulous debris and vapors, capturing stellar light with such prowess that plant-based energy capture seems rudimentary. Data retention units etch details into durable crystal grids resilient to cosmic rays and wild heat shifts. The stronghold endures blasts of ionized fury as gigabytes of packed knowledge transfer amid apparatuses blending physical form and power. Drawing on solar rays for demanding computational tasks underscores the colossal energy demands confronting any cosmic messaging network. Sending out pulses over galactic expanses demands power outlays that challenge even star-level supplies. The October 2025 alignment could mark the prime period when sun flares, world positions, and catcher sites align for peak performance in data relay. Our world's electromagnetic aura acts as the spark for this whole speculative process. From the 1920s onward, Earth has been spilling radio waves into the void at growing speeds, forming a ballooning zone of man-made emissions that now stretches approximately, extending 100 light-years outward in every direction. Our radio signals serve as unmistakable signs of advancing technological awareness to any surveillance setups in that zone. This could act as an initiation ping, potentially rousing long-dormant relay grids set up ages ago precisely for such detections. In light of this, the alignment between humanity's tech progress and the fresh influx of odd cosmic intruders gains deeper meaning. Should robotic watchers have picked up our initial broadcasts years back, it would take considerable duration to release probe fleets from remote bases, traverse the void between stars, and sync up with nearby relay setups. Today's surge of arrivals could mark the reply stage in a dialogue sequence triggered by our planet's own radiated waves. However, hard evidence cuts through these fanciful ideas with unyielding reality. There's no trace of the focused radio bursts that a real star-spanning exchange would probably generate. Measurements show no odd speed changes hinting at deliberate drives or orientation shifts. Both items' makeup and motions fit squarely into the realm of ordinary comet events, though pushing the fringes of the unusual. NASA's stance remains firm. Data so far backs organic origins over engineered ones for these interlopers. Experts at AY stress that bold assertions demand robust proof. And even with their quirky traits, neither 3i Atlas nor SWAN R2 shows marks that clearly surpass what cosmic forces might forge in ideal setups. The puzzle of, if artificial, then who dispatched them, spins off into countless guesswork trails, shedding light more on our mental tendencies than on extraterrestrial guests. Maybe these are dispatches from humanity's tomorrow, relayed rearward via tweaks to spacetime, enabling data to flow against time's arrow as well as through space. Or they could stem from separate branches of evolution that cracked star travel eons past and have since tracked smart's rise across our neighborhood in the galaxy. Other possibilities cast the pair as parts of a hoary machine web built by societies that conquered the stars well before our world coalesced, only to fade away, bequeathing just their watch and messaging gear. Under this view, we're not facing living minds, but relics of tech from races that evolved beyond or wiped out themselves in antiquity, their machines still running scripts sans oversight. Testing the feasibility of any star relay theory means crunching energy costs and signal mechanics that challenge belief under close math scrutiny. Sending steady beams over star gulfs calls for output levels rivaling chunks of a sun's total power. Picking them up even requires collector dishes spanning sizes akin to worlds. The setup demands for true cosmic comms grids outstrip the output of nearly any imaginable society. Still, such hurdles tie solely to tools rooted in our present grasp of science and tech. Races fluent in star hopping could rely on rules rendering our notions of power and messaging as outdated as beacon fires to those wielding digital cables. Feats that look unattainable through last century's laws could be everyday for beings versed in this era's insights. In the same way, what we can do now would strike earlier observers as utterly beyond reach. To those hailing from previous technological ages, the relay theory offers a compelling storyline, turning seemingly haphazard interstellar meetings into deliberate acts of data collection and exchange. It posits that our species has surpassed a key milestone in tech advancement, rendering us noticeable to advanced minds scanning the cosmos for budding civilizations. This idea assures us of companionship in the universe and vigilance from afar, suggesting our progress is under watchful eyes and possibly subtle direction from entities functioning on vast, almost inconceivable levels. Yet, it compels us to embrace bold assertions supported by data that stays frustratingly mundane, even with its peculiar traits. The theory calls for orchestrated efforts without verified links, intent where happenstance yields easier answers, and deliberate cognition where physical mechanisms provide solid bases for explaining what we see. The gathering in October 2025 stands as a pivotal trial for this relay concept. Should real information exchange happen among the incoming objects, it ought to show up during their nearest passes by the sun, when power sources are at their height and transmission opportunities align best. The real hurdle is separating routine comet behaviors from signs of tech systems handling data amid intense heat and radiation. Suppose the transfer wraps up just as our observatories lose sight, obscured by solar brightness right at the height of this imagined procedure. We could step out of that October quiet with little beyond improved data on vaporizing ice and particle flows. Alternatively, we might face proof that our star system acts as a relay point in vast interstellar networks. Under this view, the relay theory recasts our sun not merely as an ordinary star but as a galactic hub for messages. The October arrivals shift from aimless drifters to purposeful couriers, finishing journeys launched from distant star clusters beyond our knowledge. Ultimately, whether this shift signals true revelation or just our innate drive to impose order on disorder defines the core enigma of today's astronomical intrigue. Part 13. The Harvesting Model, Energy Reserves and Extraction. Our sun blazes with the pent-up fury from 12 billion years of atomic reactions, transforming 4 million tons of mass into radiant output each second, a mechanism so essential to life that we seldom dwell on its immense force. But suppose our central star does more than stabilize the solar neighborhood. Envision it as an interstellar refueling depot, yielding rare fuels and power types that advanced societies reap on timelines spanning thousands of years, not mere human spans. Picture 3I Atlas and Swan R2 as parts of a robotic extraction mission, reaching our sun not by chance, but via routines set eons ago, well before humanity arose from the African plains. The compact body acts as a scout and overseer, gauging solar emissions and ion states to maximize gathering yields. The bigger structure rolls out intake mechanisms masked as typical comet features, drawing off power and substances from the sun's upper layers through devices blending advanced tech with fundamental laws. This harvesting model urges us to rethink the dazzling comet shows we witness as veiled industrial endeavors. Swan R2's sweeping tail, spanning wide sky arcs, may hide crafted electromagnetic channels that direct solar particles into concealed processors nestled in its seeming natural envelope. The tail's opposition to the sun, which we chalk up to simple deflection by particle streams, might instead be directed venting from stellar energy harvesters running at immense proportions. Such endeavors would overshadow even the most ambitious human industrial projects. These imagined magnetic gathering apparatuses would have to function with remarkable finesse to evade our ever more advanced detection tools. Yet, highly evolved societies could have perfected the skill of harnessing natural phenomena instead of opposing them, developing innovations that amplify and guide inherent processes rather than substituting them with blatantly synthetic substitutes. What we perceive as typical comet activity could in fact be the refinement of innate ion propulsion methods aimed at gathering resources. The principles behind such extraction efforts delve into domains where contemporary human knowledge starts to falter. Envision networks of minuscule wormholes, briefly held stable by the intense gravitational and magnetic influences present close to star surfaces. These tiny pathways through space-time might enable instant relocation of gathered substances over vast interstellar expanses, bypassing the requirement for traditional drive mechanisms to ferry procured goods back to remote user societies. The powerful fields essential for sustaining these wormhole arrays would occur organically solely in settings like stellar atmospheres, where magnetic intensities soar to thousands of times greater than Earth's surface magnetism, and gravitational pulls near the thresholds where relativity's impacts turn pronounced. Our sun's October visitors could be situating themselves to capitalize on these distinctive physical traits during a narrow time frame when field arrangements align ideally for unconventional physics uses. Pulsing extraction activities might adhere to patterns linked to the sun's rotation and fluctuations in its magnetic fields, generating sequences of illumination and obscurity that our sensors would log as ordinary variations in luminosity. The sun's 27-day rotational cycle sets inherent tempos in magnetic alignments and plasma thickness, which intricate collection setups could leverage for peak performance. October 2025 could mark a prime extraction phase, shaped by extended patterns in solar dynamics and magnetic layouts. The makeup of isotopes in the solar wind offers yet another viable focus for cutting-edge extraction endeavors. Our sun generates helium-3 via its nuclear fusion, yielding a light variant that experts in human fusion power view as perfect propellant for next-generation reactor setups. The inherent solar wind disperses this isotope across the solar system at levels too dilute for human use, though highly refined isolation and enrichment methods might yield practical amounts on near-star passes. Aims for resource gathering could go further than mere fuel procurement, encompassing rare states of matter and energy unique to stellar realms. The blistering heat and compression in stellar lower atmospheres might facilitate the creation of unusual material forms, such as quark-gluon plasmas, magnetic monopoles, or additional conjectured entities that might function as power supplies or fabrication components for societies spanning galaxies. Analogies from human resource pursuits offer frameworks for grasping how star-based extraction could unfold. Early humans tracked seasonal movements to tap into fleeting clusters of wildlife, nourishing flora, and unprocessed supplies. Today's industrial societies build enduring facilities beside coal seams, petroleum reserves, and ore deposits, which dictate urban placements and transit routes. Star harvesting embodies the natural progression of this approach to astronomical proportions and power assets. The auditory aspects of these ventures strain the limits of human creativity. Amid the void of space, sound waves couldn't travel from these speculative operations. Harvesting mechanisms could generate unique electromagnetic signals that advanced societies might recognize through specialized decoding techniques. Low-frequency radio pulses, remote snaps from magnetic flux reconnections, unleashing pent-up power all converted into electromagnetic events instead of sound waves. For any legitimate resource-gathering endeavor, sustaining station-keeping would require ongoing adjustments to orientation and location amid the intricate gravitational and magnetic influences prevalent in star systems. Such demands would yield observable traces in the entity's paths and spin dynamics, which our tools ought to pick up if they exist. The lack of these traces in recent data challenges ideas of ongoing extraction activities. Still, we should recognize the boundaries of our sensing technology when facing innovations potentially millennia ahead of our own knowledge. Setups that hold steady using tweaks to nearby magnetic zones could emit signals so faint they slip under our detection limits. What we see as typical comet motion might in fact be the meticulous carrying out of elaborate industrial routines. The moral dimensions of pulling resources from stars spark deep inquiries into ownership and boundaries across the universe. If sophisticated societies regularly draw power and substances from stars across the galaxy, is our sun shared communal assets? Or does our orbiting presence around it assert a kind of domain? Might extraction efforts regard developing groups like ours as proprietors, rivals, or mere insignificant life forms? Distinguishing actual comet actions from hypothetical extraction markers is essential for assessing these possibilities. Standard ion tails stream away from the sun owing to radiation push and interactions among charged particles, adhering to established physical principles. A true extraction process would have to navigate these limits or trigger noticeable deviations in tail shapes and plasma dynamics. Current readings reveal ion tail patterns aligning with models of natural comet-solar wind exchanges. No irregular speedups, no breaches in anticipated tail directions, no signs of engineered magnetic fields exceeding standard plasma effects. The spectral profiles we observe align with recognized molecular compounds experiencing routine reactions under solar warmth. Should star-based extraction be underway in our system, we'd anticipate spotting non-Keplerian paths as gatherers adjust to shifting solar states. The missing such indicators in our orbit records for 3I Atlas and SWAN R2 implies that guiding influences on their paths stem from gravity alone, not engineered means. Yet the extraction concept holds enduring fascination because it recasts chance stellar meetings as parts of an immense industrial framework stretching across distances and eras. It implies our sun fulfills roles extending far past fueling earthly existence, that our star setup joins vast economic webs operating at scales beyond our grasp. The October 2025 alignment turns into an instance of interstellar trade, not just orbital physics, with each interloper fulfilling distinct functions in material gathering efforts timed well before humans pondered celestial glows. If the sun functions as a hub in some galactic supply chain, how often do harvesters link up here routinely, and what secrets do they bear off into the vast darkness of space? The solution could be etched in the flames and ionized gases of our sun's outer atmosphere. Only minds advanced enough to separate random cosmic processes from intentional extraction in the swirling interplay of particles and forces around every star could decipher it. Part 14. The battle unfolds. Rescue, recovery, or elimination. Concealed in the intense light of our sun, beyond the reach of earthly observatories and shaped solely by creative vision, a gripping tale might reach its climax in October 2025. A stellar showdown brewing ever since two enigmatic objects first entered our skies. Three possible outcomes emerge in this realm of conjecture. Each one recasts our puzzling intruders not as aimless travelers, but as key players in a grand contest over dominance, knowledge, or interstellar defense. The rescue narrative emerges as a tale of high-tech deliverance, with SWAN R2 showing up not independently, but as an urgent aid to the beleaguered 3I divided by Atlas. Under this view, the Deep Space Traveler isn't a fully operational device, but a compromised explorer. Its odd chemical traces signal breakdowns in its machinery, not some alien makeup. The nickel releases, lacking any iron traces, could point to structural damage or malfunctions leaking out fabricated substances as the vessel fights to keep core functions running. SWAN R2's striking exit from behind the sun gains fresh significance as a crisis intervention. Its impressive tail formation might conceal the swift rollout of salvage gear and balancing mechanisms. The huge comet's path sets it up to cross 3I, divided by Atlas right during the intense solar pass, when heat and radiation might finish off the last working parts on the struggling far-flung vessel. Such a salvage effort would demand exact synchronization and teamwork that could pass for ordinary orbital pulls. SWAN R2 would have to align speed and course with 3I divided by Atlas while releasing capture tools hidden as comet vapor. The mission could entail swapping vital components, pulling out memory banks, or supplying energy and survival aids to any survivors who endured long-haul spaceflight just to hit snags nearing our star. Other viewpoints point to a recovery setup, where SWAN R2 acts as a gatherer instead of a savior, coming to collect insights or reclaim gear from a device that's finished its task. 3I divided by Atlas could be a scouting outpost built to collect targeted details on our solar setup, with SWAN R2 as the roaming vault and transport that hauls the amassed intel home. This pickup process might feature the bigger body absorbing the tinier one, looking to our sensors like a crash or breakup. Yet instead of ruin, this seeming engulfment would mark the triumphant reclaiming of spy resources after objectives met. The peculiar schedule of both bodies' sun grazes offers prime windows for info exchange and hardware retrieval, all while dodging scrutiny from ground telescopes. The demands of cosmic spying across stars might call for precisely this kind of phased effort, using throwaway scout units for one-off jobs. The huge power drain of star-hopping travel renders it impractical to haul back minor vessels to base. However, bigger hauling ships could smartly consolidate findings from various finished ops. While adhering to paths that allow for an eventual return to their origin, the purge hypothesis offers the most ominous view of the October rendezvous, with Swan R2 appearing not to support 3I Atlas, but to eliminate signs of its journey across our solar system. In this perspective, the interstellar object acts as a signal or relay device that has surpassed its intended limits, possibly by sending data to its overseers, or by exposing its constructed essence via noticeable traces. Swan R2 then serves as the eradication team, charged with wiping out proof of advanced tech presence before developing human awareness can secure irrefutable confirmation of non-natural origins. The cleanup process would extend beyond merely dismantling 3I Atlas, involving the scattering of its fragments in manners that prevent any thorough examination. Sophisticated breakdown methods could break the craft down to basic particles, dispersing them so completely that no hint of their engineered composition survives. The schedule for this imagined erasure aligns with precise assessments of terrestrial detection abilities and the impending loss of visibility as both entities dip toward the sun's glare. By staging the purge when ground telescopes on Earth can't monitor the action, the Erasure Squad guarantees that no human devices will document the demolition or the handling of remnants. Every hypothesis demands that we rethink the dazzling comet-like shows we witness as veiled maneuvers employing tech that blends physical laws with engineering concepts beyond our current grasp. The vivid tails and growing comas could conceal directed energy tools, material dissolution devices, or unconventional drive systems that work by altering solar winds and magnetic influences. Yet these vivid explanations must grapple with the enduring truth of data from observations, which reveals nothing pointing to disputes, teamwork, or engineered involvement. Both entities persist in orbits shaped by gravity alone, exhibiting spectral patterns matching the vaporization of natural ices and the release of dust. No unusual speed changes hint at deliberate control. No radio signals suggest powered machinery or signaling gear. Mars stands as our sole possible onlooker to any developments during key close approaches, thanks to satellites circling it that are set to track 3I Atlas on its October 3rd pass. These automated sentinels bear tools tuned for world studies over spotting unusual occurrences, yet they could record signs of real exchanges between the intruders that go beyond ordinary motion. The European Space Agency's orchestration of Mars observations gives us our strongest chance to keep watch when Earth scopes can't follow the objects amid solar interference. Still, the constraints of current Mars satellites imply that just the most striking shifts from predicted normal paths would register at such ranges. Delays in signals from Earth to Mars hinder instant oversight of any supposed clash situations. The 12 to 24-minute lag for transmissions ensures that any Earth action or reply would come too late for happenings lasting minutes or hours. We stay as sidelined watchers of events playing out between Mars and the Sun. The draw of clash narratives mirrors our inclination to frame unclear occurrences within known storylines of battles, outcomes, and one side's victory over the other. Such compelling setups deliver a sense of fulfillment by turning random celestial alignments into deliberate maneuvers. Even if those maneuvers demand demolition over creation, once the illumination returns and our scopes can once again follow the intruders, shall we detect the identical count of bodies that vanished behind our star? Will their paths, makeup, and movements align with forecasts from standard comet theories? Or might we face proof that the cosmos harbors disputes and outcomes unfolding on magnitudes that overshadow human perception and test our grasp of what intellect achieves when it functions far from earthly constraints? Human Scrutiny Installment 15. The Hush of October. Detection devices quiet down sequentially as the intruders plunge toward the solar blaze. Blinding radiance. Observatory streams stutter and dim. Coronagraphs overload with brilliance. The most stunning spectacle in our stellar vicinity slips behind a veil of hydrogen inferno, bequeathing us merely recollections, conjectures, and the steady pulse of atomic timers awaiting disclosure. In official labs and academic watchposts globally, stargazers collectively pause in anticipation. Social networks hum with layperson hypotheses and creative renditions. The void of information nurtures every conceivable notion the mind can summon. During this imposed quietude, all hypotheses seem equally viable. Each viewpoint bears the gravity of possible reality. The array of results unfolds ahead like scenes from an incomplete movie. One entity reappearing, shifted in hue or luminosity, irrevocably transformed by its stellar brush. The counterpart surfacing fainter than anticipated, or maybe not surfacing whatsoever, devoured by powers beyond our gauging or grasp. Coronagraphs could unveil a fragile halo of debris where a lone voyager once passed, evidence of some stellar exchange finalized in seclusion. Or maybe everything stays unaltered save for our thirst for significance. Our craving to discern intent in the ballet of gravitational forces and the verse of evaporating frost. The true course demands steady watching and precise gauging. Swan R2's viewing period crests in late September and October, granting hobbyist skywatchers their prime opportunity to behold its dazzling tail arcing through twilight heavens. 3i divided by Atlas will exit solar alignment in December, assuming our calculations prove accurate, enabling expert tools to continue their meticulous recording of its molecular traces and path development. Existing data consistently suggests ordinary occurrences, a pair of extraordinary comets whose temporal overlap reflects the precision of orbital dynamics rather than orchestrated cunning. The Reuven scientific value resides not in validating our boldest fancies, but in gaining insights into the birth of distant solar systems, the makeup of untouched substances from our galaxy's fringes, and the mechanisms that mold bodies amid our sun's intense rays. Still, within the space between sighting and analysis, amid the lull between readings, narratives sprout and thrive. We are beings wired to spot designs in a cosmos expansive enough for both routine laws and astonishing prospects. The October hush transforms into a backdrop where we cast our profoundest inquiries on intellect, intent, and our role in the stellar hierarchy. If an age-old device honored a rendezvous at our sun, what might it encounter in our modest galactic nook? A nascent planet nurturing an inquisitive race only starting to stretch toward the heavens, already saturating the radio waves with the buzz of society. It might just locate precisely what it sought, or it could stumble upon something unforeseen in the intricate harmony of human aspirations and dreads enacted against the vast canvas of the cosmos. As December's glow brings our enigmatic travelers back into sight, as the devices pick up their quiet updates on location, speed, and light patterns, we'll finally uncover the truth behind the mystery that's reverberated across 14 volumes of awe and conjecture. Comet, fortress, or response, for now we linger in the hush of October, held in the orbital pull of our sun, pondering the narratives the void could be etching. In tongues we haven't yet deciphered, the cosmos guards its enigmas closely, yet it grants insights to those who endure.